our work. So to think broadly and as well as deeply. So in terms of astronomy, a lot of the work that I've done has focused on using the Kepler data set to make inferences about populations of exoplanets. And you might be thinking to yourself, didn't Kepler break a decade ago? Why are you still working with that? So that means we've really been in a very like modeling and technique limited regime rather than a data limited regime. As of a few years ago, with Gaia Data Release 2, we're no longer limited by stellar properties, which for the first 20 years of exoplanet science was basically the limiting factor on everything that we did, is we just didn't have stellar characterization that was good enough. We now have great stellar characterization for basically every star, so it became prudent to go back and think about some techniques that we've been doing for a long time, in my case, particularly transit modeling, and say, okay, what are the last 5 or 10 or 20% improvements we can get out of these models in order to get some really subtle inferences we wouldn't have been able to do otherwise. And with the specific problems that I've thought about, that ended up leading to a lot of thinking about degeneracies and covariances and posteriors and ways that we can explore, really complicated geometries and topologies that standard techniques do a good enough job until you're trying to get below 10% precision, and then they're just not sufficient enough. So all that preamble being said, I want to get started with what's maybe the most basic problem we can do, which is fitting a line to data. I know it's early on day 3 on the half day and it's rainy, but I want this to be fairly discussion-based. So please, everyone in the audience, tell me all of the things that you need to think about when you're fitting a line to data. Yeah. Yeah, how much data you have? What else? Yeah. Yeah, what model you're choosing. Can you say a little bit more about that? Sure, exactly. Like what functional form you use for your model. Yeah. Mm-hmm. How much uncertainty? What else? Yeah.
Is the uncertainty like homoscedastic or heteroscedastic different between the state of...
Great, exactly. For those that don't know, heteroscedastic is a word that means the uncertainties are varying across the measurements, often increasing in one direction or another. Yeah.
Whether you should be doing that.
Yeah. Anything else? Any other thoughts? Great. Yeah. Mm-hmm. Yeah. Do our standard, chi-squared minimization or something else. Yeah. Any other thoughts, things that we need to think about? Yeah.
What do we want to get? Do we just want like the best fit? Are we curious about like the uncertainties that...
Yeah, exactly. Yeah, what's our goal? Do we just want a point estimate? Do we really care about how broad our estimates are? Cool. This is about what I was hoping would happen, is we get some thoughts, and then there's a whole bunch more that we need to think about when we're building a model, right? So I think everyone nailed the top left quadrant pretty well in here. What physical models are we thinking about? That makes sense, right? How do you parameterize your model in terms of, a polynomial, a sinusoid, et cetera, et cetera. But there are all these other things that we need to think about when we're actually fitting a model in practice. And I will say these categories are, fairly arbitrary. There's a lot of overlap between them. I've broken it down this way largely to orient the lectures I'll be giving over the next few days, right? So on the statistical side of things, right? Some people mentioned, are the uncertainties uniform or not, right? We also want to think about how the data were collected, right? Are the data actually independent? Is there going to be correlated noise in the data that we need to model? And do we need to actually explicitly account for how we get our data in the first place, right? As astronomers, we're pretty good at designing surveys or experiments that minimize those sort of systematic and observational biases, but sometimes you still need to fold it in and really think about it. And then in terms of the model specification, a lot of times in practice, you can have two equivalent models, right? They're mathematically equivalent, but how you actually describe the functional form of the data can lead to very different efficiencies in how you draw samples. I'll give a couple of specific examples on that in a moment. But even when on paper you're doing the exact same thing, it can lead to very different results. And then we also want to worry about, what are our priors? Do we test for convergence? I think most people have heard of those things. We'll get into those in a little more. And then our topic for today is talking about the different tools that we use for actually sampling from the posterior. Right, maximum likelihood is something I think you guys have covered the last couple of days. Kind of the simplest brute force thing you can do is a grid search. You just manually, walk through your various parameters and see what you have. And then, today I'm going to be focusing on talking about different MCMC methods that iterate on the Metropolis-Hastings algorithm, as well as nested sampling, which is a conceptually very different way of doing things. It looked like we might have had a question over here. No? Okay, great. So returning to our problem of fitting a line to data, pretty much every time that I fit a model, I'm thinking in terms of a generative model. And what that means is you want to think about what processes are actually creating the data that you're observing. And so to give you an example, I was working with a colleague who was trying to understand macro turbulence of stars. And he was using some software that output rest frame stellar spectra at the native resolution of different instruments. And he was then taking those and applying some extra line broadening and shifting to it to capture Doppler shifts and all the things going on in the stellar photosphere. But we talked for a while, and what we realized is that wasn't really the data generating process, because what was going on is he had the model that had these rest frame stellar spectra at a certain binned resolution to match the telescope, after which he was adding in the stellar physics. But if you think through the causal chain of events, what's going on is the star creates some spectrum that's at effectively infinite precision, quantum effects notwithstanding. And then that rest frame spectrum is modified by everything churning on, going on the star. And then at the very last step, does it interact with the telescope and the detector and get binned down to a certain resolution. So, he modified his code to, instead of producing these stellar spectra at the start at the resolution of the telescope, producing it at a very high oversampled resolution, then doing all of the physics he was trying to investigate, and then binning it down. Right? So that's what I mean when I say building a generative model. You need to actually think of the processes that are happening because it can really make a difference. Okay, so, right, this is our line. This is one way that you can model it right here, we have this little add-on with the S squared, which counts for, maybe some issues that we have where the uncertainties weren't measured properly. But from that discussion we had a few minutes ago, what I wanted you all to take away is that we're making a lot of implicit assumptions that you might not even be aware of whenever you're building a model, right? Even here, there's one assumption we haven't mentioned yet, which is that we're using our standard Gaussian likelihood, right? That's going to be our default, but again, it's an assumption you're implicitly making that it can be really helpful to explicitly think through what you're doing. Okay, so if we run this through a model, we get all of these nice, simple Gaussian posteriors. Great. We love seeing Gaussian posteriors. When we're in this situation, basically our choices don't matter, right? You can look at this data set and you can fit this essentially any way you want, and you're going to get a good result because we're very constrained by the data. But, okay, so before we get into the more complicated posteriors, one last comment on these Gaussian models. The way I explain the work that I do to any of my friends and family who aren't in science is I tell them basically I try to deal with really dumb Roombas, just robot vacuums that are trying to explore rooms, right? If you got a Roomba that's trying to explore a circular and elliptical room, there's nothing for it to get stuck on. It's the same distance in every direction. You can have the dumbest Roomba in the world, and it's just going to find everything and pretty quickly, right? It's cheap. There's really nothing you have to do. But with real data, we have these much more complicated posterior topologies that we're going to be exploring, right? And if you think about it, if you have a dumb Roomba, it's not going to be able to explore this, right? If you have strong curvature, it might never get into this very narrow bit right here. It might get stuck in the wider bit. Similarly, if you have a multimodal situation, even if they're connected by a thin region, you might stay in one or two of the other rooms and never get to the other one. You might just never find a region of your posterior space. And the fundamental problem is we don't know what this topology looks like at the outset. If we did, we wouldn't have to run our model. That's what we're trying to find. And then one last thing is, even if we do have a nice, simple, multidimensional Gaussian with not too strong of covariances, as you increase the number of dimensions, you run into these, thin degeneracies. Anyway, this was similar to the problem that you did yesterday with the filling. And, as you go to more and more dimensions, more and more of the volume moves further and further out in this, multidimensional sphere or multidimensional annulus. So even with simple problems in high dimensions, they become difficult to sample from. This is a term you might see, the typical set, right? It effectively means, your volume element near the maximum likelihood becomes infinitesimally small in high dimensions. And so you're moving out and out further and further away from that. And you can think of that as kind of like, if you have 100 dimensions, your chances of all 100 simultaneously moving towards the likelihood become negligibly small. So that's all a very hand-wavy explanation of what typical set is, rather than a mathematically rigorous one, but hopefully it helps to build some intuition. Okay, so this is what we're trying to do, is sample from these complicated posterior topologies. And there's two main ways that you can go about doing this, other than just choosing a different problem. One, which is what we're going to do today, is talking about changing your sampler, right? Changing the machinery you're using to actually explore. And two is we can apply various different transformations to warp these to look more like a Gaussian. Kind of stretch or mold them. And that's what we're going to talk about on Friday. Yeah.
That's like what you mean by posterior topology is?
Yeah.
I guess I'm like, so you showed the one you think that was Gaussian and that looked really nice. So like, does it look like when it's complicated, I guess?
Yeah. So let me draw some. All right, so when I say, just realized. Now I'm coming through the microphone. Was that before? Great. Okay, cool. Is it better this way? Worse this way? Better? Okay, cool.
Also tilt forward towards the camera, so at least a little. I don't know.
Sure.
Thank you.
Showing up on camera?
Yes, I'll take a picture of it later.
we can rotate more. It's an easy thing to do. Better? Okay. Fast people here can see. I'll do my best Vanna White impression and rotate the board in a moment. All right, so when I say posterior topologies, what I mean is basically just think about the corner plots in your head, right? So in a simple Gaussian corner plot, right? It's a simple posterior topology, right? And when I'm using the word topology a lot to kind of have different language from what we might use for other parts of the problem. So think about a topographic map, right? If you have a mountain, it's going to look kind of like this. But if you have ridges, you might have like very closely lined ones, and then it might, be very curving and very complicated, right? So if you've ever gone hiking and looked at a topographic map, that's what I mean by topology. So a more complicated corner plot would be something like, say you have some curvature that then goes from being broad to being very narrow, right? So if you were to draw samples here, they look like this, and then, it gets very sparse out here. So that's what I mean when I say complicated topology. If you've got this region where it kind of, if you squint, looks Gaussian, it's broad, it's easy to explore, and then you get this long, thin tail like this. You can also have a complicated topology, right, like the egg box topology. You've got these 4 isolated modes. Essentially, anything that looks less like a circle is complicated. You could even imagine something that's like, I don't know what would cause that, but that would be really hard to sample from. Cool. Okay, so this is what we're trying to do, is sample from these complicated topologies. So just to remind everyone of Bayes' theorem, right? These are the 4 components. There's the posterior, likelihood, prior, and evidence. MCMC attempts to directly generate samples from the posterior, which is a difficult problem if the posterior is unknown, which it is if we're applying an MCMC algorithm. Right? The evidence for now, you guys can just ignore. You can think of it as just a normalizing factor. So we'll get back to that when we talk about nested sampling. And the likelihood you choose. So it's, in a sense, trivially easy to calculate because you know what it is. And same with the prior. You define what the prior is. So you can set that. So the posterior is the only unknown in this model. And I will say one other thing is Bayes' theorem always has this implicit assumption that you're not just given some set of parameters theta, you're also given some model. I'm not going to include that, given M, because it just, muddies up the notation, but that's always there, as it's assuming some particular model. Any questions on the notation? I'm going to be trying to stay consistent with the notation throughout, but I know it might be different from what you've seen the last couple of days. Okay, cool. So you all have already seen random walk Monte Carlo. This is essentially the basis for every MCMC algorithm we're going to use. They're all just iterations on this. So just to remind you of how we do this, we choose some initial set of parameters theta, and then we loop over some number of iterations. You have some proposal distribution Q. You draw a new set of parameter values from that distribution. The simplest would be, you have just a small multi-dimensional Gaussian centered on your parameters. You draw each of the parameters, and you say, okay, let's calculate our acceptance ratio based on the likelihood. Is it going to be a better or a worse fit? We don't only want to move uphill towards the better fit. So we generate a random number, and we say, is this likelihood ratio, do we beat this random number or not? And I've quietly not included some, censoring of the data to make sure if we have a likelihood ratio greater than 1, right? That's all, or that's always accepted. But conceptually, this is what's going on. Any questions about the standard MCMC algorithm before we move on? You guys spent a while on this already. All right, cool. So random walk Monte Carlo is great. It's conceptually the foundation of everything we're going to do, but it can be very slow, especially when you get into high dimensional or complicated problems. So there are all these different variations that have been developed that are essentially just trying to be smarter about how you propose your steps, right? The fundamental problem of random walk Monte Carlo is it's random. You're just stumbling around blindly, hoping to get to a better position. But these various methods all do different things to try to infer something about the local geometry of the space and make smarter steps. So the simplest variation is Metropolis Hastings, which just is a small variation on random walk, which allows you to make asymmetric proposals. Gibbs sampling okay. I'm not going to go through the whole chart because we're going to go through each of them in detail. I will say that this cluster of 3 right here, differential evolution, affine invariant, and parallel tempering, those are all a class of samplers called ensemble samplers. Everything else works with just one walking chain. Usually we'll run it with multiple chains so we can test for convergence. But these ensemble samplers, you have to run a bunch of chains in parallel, and then the chains talk to each other and learn from each other. Okay, so Metropolis Hastings, it's just this slight change to the acceptance ratio, which allows you to account for asymmetry. You're probably not going to really work with Metropolis Hastings ever in practice because it doesn't do that much to speed things up. The original algorithm was written in the 50s, I think, so there's been a lot of work done since then. All right, so the next thing you might think is, okay, if we're in a high-dimensional space, it might be unlikely that if we draw all of our, say, 30 parameters at once, that we're going to move to a higher likelihood. So you can get around that by just doing one at a time and taking these square steps to get towards the maximum likelihood and explore the space. Conceptually pretty simple. Again, probably not something you're going to use in practice all of that much, just because there are better, more sophisticated algorithms. But you might find some specific problem where the context of the problem demands that you think about separating the parameters into different groups, right? It might be, you know, something, say, about the topology where you're like, you know, you move in this set of parameters a little bit and explore things, and then move in this set of parameters. But again, that's going to be pretty specialized a lot of the times. I've not ever personally run Gibbs sampling for any real problem, but good to know that it's there if you need it. All right. And then there are ensemble samplers, right? And these all use various different ways of getting these walkers to talk to each other to make smarter proposals. So differential evolution and affine invariant sampling are conceptually fairly similar. They use these genetic mutations or stretch moves where essentially you take this one walker here, right? So this is your walker that we're moving right now. And you find some reference walker here. And we say, okay, well, we're going to move along the line between those two walkers. You can see if you drew lines between all the different walkers, that gives you some sense of what the geometry looks like. It allows you to make smarter steps based on the positions of all of the different walkers and starting to learn what the geometry looks like. Affine invariant sampling does a very similar thing, except instead of moving based on moving around the position of the current walker, you're taking this walker and then you're moving around the position of the reference walker. For anyone that's used Danforth and Mackey's MC package, which is a lot of people, it's very, very popular. It's over 10,000 citations the last time I saw it. That's an affine invariant sampler. And the main thing these two do is they're good at moving when you have strong covariances between parameters. They don't always work as well if you end up getting these like very curving topologies here. But they are very good if you go from, say, you know, a non-correlated Gaussian to a more correlated Gaussian. And they're pretty good defaults for things to try for samplers. Affine invariant has the benefit of having, you know, a lot of very easy to use machinery built up around it. And then parallel tempering does something pretty different, which is that you give each of the different walkers a different temperature. Right? So you can think of this analogous to statistical mechanics, where the hotter chains take bigger steps, and the smaller chain and the cooler chains take smaller steps. And then periodically, the different walkers will swap positions, and this allows you to do a much better job of exploring these posteriors where there might be, you know, wide regions and narrow regions, because for the wide regions, you need the hot walkers to, you know, traverse big distances. For the cold regions, you need for the narrow regions, you need the cold walkers. Right? Okay, so again, conceptual overview, I haven't really, you know, mathematically justified any of this, but again, the main thing I want you all to take away from this is knowing these tools exist so that you can use them if the need comes up. Okay, so any questions? Oh, sorry. Yeah.
So is that the parameter space?
Yeah, that's an illustration of the parameter space we're trying to draw from. So this is the same as this, where if you think about it in terms of a corner plot, where the highest probability region is around here, right? So if we've done a perfect job of measuring, let me cross it down to one dimension, make it a little simpler. So say we have some parameter x naught, right? And we just know that this is the value that we're trying to estimate. And from our MCMC chains, right, we run those and we calculate and we get we get a lot more measurements estimated here, a lot fewer out in the tails, right? And we could plot that as a histogram and say, okay, there's a lot more like this, right? And so our histogram of measurements would build up like this, and generally we'll draw that smoothly like that, right? So based on our measurements, we say, okay, we have a higher probability that the true value lies somewhere in here. And so in 2 dimensions, it just looks like this. Great, okay, no problem. Okay, so yeah.
Sorry,
No need to apologize.
could you clarify more about the differential evolution? Is it just that like the current walker is considering the distances from previous walkers? Or am I misunderstanding like what it's doing?
Yeah, so with random walk Monte Carlo, you just like take this one walker and not know anything else about it, and you draw a little Gaussian around it, and you would step in some direction in that Gaussian, right? With differential evolution, it says, okay, let's pick some reference walker. Now we know what direction we want to move in, because we're going to move towards this other walker. And we also have some idea of how far of a step we want to take because we know how far that other walker is around.
Okay, got it.
Yeah.
Thank you.
No problem. Any other questions on ensemble samplers? Yeah.
Do you have like one that you recommend using generally, or is there one that you recommend like not using, especially if they don't know what distinguished space looks like?
It's really problem dependent. That's one of the main takeaways is there's no single sampler you can use in any case. I tend to start with Hamiltonian Monte Carlo, but that's largely because I really like PyMC3 as a package. It makes it very easy to build models. Usually I use either Hamiltonian Monte Carlo or nested sampling in my own work. Parallel tempering can also be useful. I've been working with a colleague that's been using that for some like astrometry fits that are sparsely sampled. But yeah, you really just kind of have to look at the problem. And usually I'll try a few different ones and make sure they all give the same result. Yeah.
You guys said earlier that some methods are better for when, or maybe worse for when there's, you said, Gaussian correlation between parameters. I mean, these things like just covariance. How is it possible to differentiate that from just degeneracy?
So when you say degeneracy of parameter space, what do you mean?
Like two, like fitting a black body, radius and temperature, both contributing to your amounts of the output. Like,
yeah, I mean, I would consider that basically the same
Okay.
problem, because when you draw your posterior samples, you're going to see covariances as a result of the modeling degeneracy. Yeah.
Also, get stuck somewhere. Is it worse to deal with whole samples at a time? Because like they're all going to talk to one that might be confused and then all look like confused. Versus running one walker at a time.
Yeah, so nested sampling is pretty good for avoiding those problems where you get one that's stuck in a different region of parameter space. On Friday, we're going to talk about some specific techniques for dealing with stuck walkers. So hold that thought. We'll get into that more in detail. Yeah.
There are cases where you can't use, like there are requirements to use a specific sampler, like I've heard for Gibbs sampling, you need to know the conditional probability between like the different parameters, and for Hamiltonian, like the posterior has to be differentiable. Is there a way to know like if the posterior is differentiable to be able to use Hamiltonian, or how do you?
Yeah, so again, it's going to come from context of the problem, right? Differential essentially means it's smooth and continuous. Right, if you've got discrete values, then Hamiltonian Monte Carlo might not be the best choice because that's not continuous. But even there, some people have done some clever things to make even discrete problems solvable with Hamiltonian Monte Carlo. One overarching answer to all of these questions is do exploratory runs to start with. Don't worry about getting the right answer immediately. Just do something that's quick and gets you a broad understanding of what the posterior space looks like, and then you'll be able to more intelligently and more knowledgeably choose what the best tool is for the job. And it really is exploratory, right? Throughout the whole process, you don't know what the answer is, so you kind of just have to try stuff and see what you see, and then adjust as you go. Yeah.
Yesterday we heard that you often throw away the first 2 steps of each random walker because you're selecting points to start off each walk. Is that also the case for these one ensemble samplers where you actually know about the other walks?
Yes. Yeah. You always have to have the burn-in phase where, we'll talk about this more on Friday, which is looking at convergence. You essentially want to get your sampler to the point where it looks like it is random walking around. If you look at, say, the position of one walker over time, you'll often see it doing something like this, and then eventually it starts like settling into some steady state. So, excuse me, you would want to, chop off all of this part because you're still getting to the starting line. Okay, I'm going to move on to HMC so that we can get through everything, and not go too far over the 45 minutes. Okay, so Hamiltonian Monte Carlo. This is a relatively new development computationally, but it's a method that I really, really like to use a lot of the time. And it's pretty clever, right? Instead of having just these walkers that are only moving around based on their current position, you give each of these particles a momentum vector. So you can really think of this analogously with Hamiltonian mechanics. And you can think about it kind of like rolling a ball around a basin, right? If you took some particle and put it right here and gave it a kick in this direction, it would roll uphill and then downhill a little bit. And there's this algorithm that's been developed called the no U-turn sampler, the NUTS sampler, that basically it explores the space and then waits and looks until when the particle would start to turn around to make a U-turn, it says, okay, that's as far as we're going to go. And the nice thing about HMC is a lot of people have put a lot of work into building up tools that will tune the problem for you, which is the HMC equivalent of the burn-in phase. Basically, the sampler needs to learn, how much momentum do I give each of these particles at each point? What is the correlation between these? And then once it figures that out, then you're off to the races and things go very, very quickly. So with all of these other samplers I've talked about before, one challenge is that you need to thin the chains after you're done, meaning it takes a number of steps to get from one position to another position where the chain has effectively forgotten where it was before, right? So, say I take a random step in this direction and a random step in this direction, maybe it takes me 20 or 30 steps until my current position is no longer correlated with that previous position about 30 steps ago, right? So it's computationally inefficient. You end up needing to throw out, 95, 99% of your data, however, whatever your thinning fraction is. With HMC, the trade-off is that, you've doubled the number of parameters that you have, right? Because everything has not just a position, but also momentum. So it is more computationally intensive per step, but you end up with these really short autocorrelation lengths where because you've given some momentum kick to your current position, you end up very far away from where you started out, and you end up with these short autocorrelation lengths of like 2. So you can use basically all of your samples. So that's why, again, a lot more mathematical overhead per step, but you end up often the actual time you spend sampling is much shorter because you need to run chains of length like 1,000 instead of length 30 or 40,000. Any questions on this? All right, so I basically already talked through all of that, so we can move on. All right, so we're going to wrap up with, so yeah, go ahead.
Is the norm to spin sample samplers? Like, is that like best practice versus like keeping everything but account like I'm like modeling your autocorrelation in some way?
Yeah, you could do either. Usually, if you've got like a really long autocorrelation length, usually I do end up thinning because then you've just got a lot of redundant data. But if you are actually exploring long enough and correctly calculating your autocorrelation length, yeah, you could just weight everything that way, and it should be equivalent. Yeah, but the point still stands. You need to run for a very long time to make up for that autocorrelation length. Okay, so coming back to Bayes' theorem, now we're going to talk about nested sampling, which everything else was essentially random walk Monte Carlo. Right? Those are all running basically the same algorithm under the hood with just different ways of being smarter about how you take your steps. Nested sampling takes a very, very different approach, whereas MCMC is focused on generating from the posterior, which is, again, a hard problem. Nested sampling is more concerned with calculating the Bayesian evidence. And it does it by generating samples from the prior, which is a much, much easier problem. Because again, you've defined your prior, you know what it is, you can draw it directly from the prior. Okay, so here's a conceptual overview of MCMC versus nested sampling. And by the way, Spiegel 2020, it's being cut off here, but you'll be able to see on the slides. If you're interested in learning about nested sampling, Josh wrote a very great, very pedagogical paper, which I highly recommend reading. That's how I learned how to do nested sampling. So basically anything you want to know, you can find there and then follow the breadcrumbs of citations and videos that Josh has put out. MCMC, sample directly, combine samples. Great, that's what we've been doing. In nested sampling, it's very different. So instead of building up with samples here, and essentially you're doing, a Riemann sum, we're just doing integration. In nested sampling, you're breaking into equal level contours based on the likelihood, sampling from each slice, and then combining weighted sampling. So you can think of it kind of like, instead of integrating your curve like this, we're integrating our curve in horizontal slices rather than vertical slices. And so the challenge there becomes determining where the equal likelihood contour levels are. So the way you do that, you start with some prior space. Right? You've got some prior volume, and you just throw down a whole bunch of what are called live points. These are kind of the equivalent of your walkers in an ensemble sampler. They're not going to function quite the same way, but roughly analogous. You throw down a bunch of live points. You take whatever live point is at the minimum likelihood, you record its position, right, what all the parameter values are, what the likelihood is, and you track that on a list of what are called dead points. You then throw down another live point. For now, let's just assume we're throwing down another live point randomly. You keep retrying throwing down that live point until you hit at a higher likelihood than the one you just removed. Right? So you can see that over time, your live points are going to be all moving towards higher and higher likelihoods. And whatever the lowest likelihood live point is, the one that you're removing, that defines a particular likelihood contour. Right? So you keep doing that. You can see that the live points are converging closer and closer to the maximum likelihood position. And you stop when you find that the live point that you've removed is moving up negligibly in the likelihood. Okay, so you might see that if we're just randomly throwing down our live points after we remove them, we're going to get exponentially less efficient as we move on. Right? Because as your volume that you're shrinking from, that you're sampling from, the likelihood contour gets smaller and smaller, you would get a lower and lower probability that a randomly generated live point would fall into that region. Right? That's this example all the way over on the left. So the challenging problem of efficient nested sampling is trying to determine what that iso likelihood contour is. And there are different ways that you can do this. One you can think is just, okay, let's just draw an ellipsoid around the whole situation. That's computationally cheap. But in this example where you got these two rings you're trying to sample from, there's still a lot of space that you're wasting. Right? And then there's the other versions where you can say, okay, maybe we want a bunch of ellipsoids, or we want a bunch of balls or cubes that all overlap. And so these are going to do a better job of honing in on what the likelihood curve is, but they're more computationally expensive to calculate. And like everything else I've been talking about, there's no one best option. You need to look at the problem that you have in order to choose what option is that you want to use to draw these iso likelihood contours. If you draw them too big, then you're going to be very inefficient. But if you draw them too small, you can run into this phenomenon called nested sampling shredding, where essentially you're getting these isolated slices of the posterior, and you've ruled out some real region of parameter space. So if you were trying to say we're back to trying to measure from some long curving posterior like this, right? If you shrink your bounding distributions too quickly, you might end up with like things like this, and then all of a sudden, right, you get these little like paper cuts. Okay, so just a little bit on the math here, right? So earlier I said that the evidence you can think of as a normalizing factor in Bayes' theorem. And it's sometimes called the marginal likelihood, because what you're doing is you are taking the likelihood multiplied by the prior and then integrating it over all possible values of your parameters. Again, for some implied model. So that's the evidence C there. You can also express it as an integral over the prior volume. Right? And one of the exercises that I have you guys doing is actually applying nested sampling. One of the steps there is you have to do what's called a prior transform. You generate samples from a uniform cube, and you need to transform those into whatever prior you're sampling from. We can talk about that as you work on the problems. I don't want to get too deep into the math there right now, but just a heads up that that's going to be the most tricky step of actually applying nested sampling in practice. Right? And so once you have the evidence, right, then we can generate posterior samples as a byproduct. Because we know the likelihood, and we can calculate the weight proportional to the prior volume that is contained within that iso likelihood contour. Right? So the nice thing about all of these Yeah, okay, I just said that. So these are a few popular implementations. I like to use Dynasty, but multi-nest and ultra-nest are also used frequently. Okay, so the question all you probably have is which sampler should I use when? And the answer is they all have their place. Other than maybe Random Walk or Metropolis Hastings, those are good for learning, but they're slow. So you probably won't use those in practice. In Gibbs sampling, you might find special cases where you know something about the geometry, you want to split things up, you'll use it there. Affine invariant, I'd say is a great default because it both works pretty well and because MC is popular. There's a lot to be said for using whatever software packages are that other people know how to use, and they'll be able to work with you and help you debug and help you understand. I honestly make a lot of my choices about how I code things just based on what Python packages I like using. That's why I use PyMC3 most of the time, is I just really like the interface. Right, parallel tempering can be good for complicated posteriors. Some packages have it built in. The astrometry problem I mentioned earlier uses a package called Orvara, which just has parallel tempering built in. That's why we're using it, is it was just easier to use the native sampler of this package rather than writing our own. Hamiltonian Monte Carlo really, really excels for high dimensional problems. So that should be your default if you have very high dimensions. But you do need to have differentiable topology. Again, a lot of work has been done with different packages that they use what's called auto gradient or auto differentiation software. You guys don't really need to worry about calculating those gradients yourself. You just need to make sure you have a problem where it's applicable. And then nested sampling is great for these complicated or especially multimodal distributions. This one of all of these probably does the best if you have isolated modes, but it really suffers from the curse of dimensionality. As you go to higher and higher dimensions, drawing those bounding likelihoods gets more and more difficult to do efficiently. And that's why I said I usually use a combination of HMC and nested sampling based on what problem I'm doing. Often I will like build my initial model in HMC because I like the PyMC interface. And then once I get a feel for things, I'll switch over to nested sampling for the final runs, provided I'm not dealing with too many dimensions, and nested sampling is a bad choice. All right, and this right here is probably the most important slide I'll show all week. These are basically all of the references that are my statistics Bibles. So I would highly recommend not only reading all of these, this one's a textbook, the rest are papers, but also finding anything else these people have written or YouTube videos they put out and just like watching them and rereading them. I probably read this paper like 3 dozen times during grad school, learning something new every time. It's everything you need to know about just fitting a line. So I would recommend going back and reading all of these. All right, and we'll leave it there.
Are there any questions before we go to break?
No, for example, if you already have an estimate from less from one sample, or where are the regions with higher likelihood, will you initialize the other samplers already in those regions?
Yeah, so the MCMC samplers, so everything but nested sampling, usually a good idea to initialize near but not quite at the maximum likelihood, right? So like basically find the maximum likelihood and then spread things out in a little ball. That's usually a good default. Nested sampling, I'm glad you asked that because this is a really important point. Nested sampling, you're not initializing from a certain point. You're initializing from the full prior. And remember, the first step of nested sampling is you throw down a bunch of live points that cover the full prior randomly. And this is why it really suffers from the curse of dimensionality is if you have high dimensions, there's more and more chance that most of your live points are going to be in these very, very sparse, very low likelihood regions of parameter space. If you have lots of dimensions, it means you're going to have a lot of steps that it's going to take until you find the high probability regions. So in MCMC problems, when you're using an MCMC sampler, if you're initializing near the maximum likelihood, then it doesn't really matter if you choose a comically wide prior, right? But in nested sampling, that can really hurt your performance, right? A lot of times we'll be like, oh, we'll just use a uniform prior and effectively set the bounds at -infinity and infinity. Can't do that with nested sampling. You need to try to choose your prior with intelligently selected bounds such that you don't want to be cutting off any of the regions of parameter space preemptively, but you want to be as tight as you can so that you're not wasting sampling time exploring. Yeah.
With Hamiltonian, it's a little bit hard for me to find an intuition of if we don't know what the topography looks like in the first place, how are we using those momentums to go into the middle of some phase?
Yeah, that's a great question. To be fully transparent, I don't 100% understand how the nuts algorithm works. But it's basically, it starts by setting some of these particles moving with certain momentums and tracking which of them go totally off the rails, right? So end up like going very, very far. They're called divergences. And then, adjusting how much momentum it's giving everything. And it's tracking what's called the mass matrix, where it's essentially this matrix that is on the fly kind of updating and saying like, okay, this is what we think the covariances are between the different parameters. And as those covariances are being adjusted, that informs, what momentum kicks it gives, and then it'll iterate and readjust what the covariance is until you're not getting all of these divergences all the time. Does that make a little more sense? Yeah. Okay. Yeah. If I didn't say it before, the tuning phase of HMC often takes longer than the sampling phase. So as you're working through the practice problems, if you see PyMC give a warning like expected time 8 hours, don't freak out. It will say that at the beginning. And then as the sampler starts to figure out what the topology looks like, it'll rapidly shrink down. And then at the end, it will just go blazingly fast. Any other questions?